Hey everyone, and welcome to The Explainer. Today we are diving into what is honestly one of the most fascinating and frankly urgent challenges in modern technology, the ticking quantum clock. We're going to unpack the exact timeline and the actual mechanisms behind the impending quantum computing threat to global cybersecurity. The countdown to Q-Day has officially begun, so let's break down exactly what that means for your data. Okay, let's just jump right in with a mind-boggling comparison to set the stage. Take a standard 2048-bit RSA encryption key. That's the exact kind of math securing your bank transactions today. A classical computer would need roughly 300 trillion years to brute force crack it. But in the quantum realm, theoretically, a perfectly stable system could shatter that key in literally 10 seconds. And even with a realistic, slightly noisy quantum system, we are looking at about 8 hours. I mean, going from 300 trillion years to a standard workday, that is a massive paradigm shift. So here's our quick roadmap for the day. We'll be looking at 1, the quantum security threat, 2, Shor and Grover's algorithms, 3, the accelerating hardware race, 4, securing the quantum cloud, and finally 5, the post-quantum defense. All right, kicking things off with Section 1, the quantum security threat, or as it's often called, the end of the trapdoor. Moving right into Section 2, Shor and Grover's algorithms, basically breaking the math. You know, modern cryptography essentially relies on a mathematical trapdoor. It's super easy to multiply prime numbers together, but astronomically hard to reverse engineer them to figure out what primes you started with. But take a look at this chart estimating the time it takes to factor RSA keys. Right in the middle there, factoring a 2048-bit key classically is just unfeasible. But if you scale up to a 20 million qubit quantum system, that completely impossible task suddenly drops to just 0.3 days. Yep, that is an 8-hour workday to crack the very backbone of our digital security. So how exactly does that 8-hour timeline happen? Well, we have to understand a concept called exponential speedup. Basically, this is an immense computational leap where the time complexity to solve a problem becomes polynomial rather than sub-exponential. In plain English, it drastically cuts down the time required to find prime factors. This right here is why Shor's algorithm is an absolute game changer. It leverages this exponential speedup to completely dismantle asymmetric cryptography, like RSA and Diffie-Hellman. And you can literally see that exponential speedup happening on this graph. Just notice the massive, ever-growing gap between that red dashed line, which represents classical computing, and the blue solid line for Shor's algorithm. As the size of the encryption key scales up on the bottom axis, classical computers just hit a brick wall. But Shor's algorithm? It stays ruthlessly efficient, completely flattening the curve. It's wild to look at. But wait, Shor isn't the only threat out there. We also have Grover's algorithm to worry about. Grover introduces what we call a quadratic speedup. This is a dramatic reduction in unstructured search times. And honestly, there's a great analogy for this. Imagine searching for a needle in a haystack. A regular classical computer has to check every single piece of hay, one by one. Grover's algorithm, on the other hand, effectively finds that needle in roughly the square root of the total steps. Because of this massive shortcut, Grover's algorithm effectively halves the security length of symmetric keys. So an AES 128-bit key suddenly only offers 64 bits of protection against a quantum search. Okay, Section 3. The hardware race accelerates, going from theory to reality. Because, let's be real, a theoretical math threat means absolutely nothing without the physical hardware to back it up. Check out IBM's aggressive roadmap for this next decade. In 2024, they're aiming to hit 5,000 gates. By 2026, we are looking at actual quantum advantage. 2029 is the huge milestone, delivering the very first fault-tolerant quantum computer. And by 2033, they're targeting 1 billion gates. So yeah, the hardware is scaling up much faster than a lot of people realize. And IBM is definitely not alone in this race. Take a look at this schematic. This is Microsoft's Majorana 1 chip, and it takes a radically different approach to the problem. Instead of traditional qubits, it uses exotic topological qubits. See, it encodes quantum information non-locally across those H-shaped nanowires. Because the information is distributed out at the extremities of the device, any local environmental noise, like stray heat or electromagnetic interference, just can't easily disrupt it. It's a brilliant intrinsic hardware-level defense against decoherence. So why does Microsoft's exotic approach actually matter? Well, let's compare them. Traditional superconducting transmon approaches, the kind used by IBM and Google, they have a pretty high base error rate. This means they need over 1,000 physical qubits just to stitch together one stable logical qubit. It's basically a brute force approach to error correction. But Microsoft's topological design, thanks to that intrinsic protection we just covered, dramatically drops the base error rate. That means the Majorana architecture requires a tenfold reduction in physical qubits. You only need about 100 physical qubits per logical qubit. It's a massive, massive leap in efficiency. Which brings us to Section 4, securing the quantum cloud. Trust no server. As these quantum machines scale up, most companies aren't going to have one in their basement, right? They'll access them remotely via the cloud, which obviously creates a massive privacy issue for sensitive data if you can't completely trust the server. The answer to this is a fascinating framework called Universal Blind Quantum Computation, or UBQC for short. It works in 3 elegant steps. First, the client encrypts their input, essentially obfuscating the data via random bit and phase flips. Second, the untrusted quantum server computes the logic completely blindly on those encoded states. It literally has no idea what it's processing. Finally, the client gets the garbled output back and decrypts it by applying selective X and Z gate corrections. It's essentially a stealth mechanism that lets you run powerful operations, like Grover's Oracle, on remote hardware without ever leaking your proprietary data to the provider. And finally, Section 5, the post-quantum defense, surviving Q-Day. Look, I know this all sounds terrifying, but we are absolutely not doomed, provided we start preparing for that 2032 to 2035 Q-Day window right now. For symmetric systems like AES-128, since Grover's algorithm halves the security, the technical defense is actually beautifully simple. Just double your key length and upgrade to AES-256. Boom, you're safe. The exact same logic goes for hash functions. Just upgrade SHA-256 to SHA-512. But public key systems like RSA, those are the tricky ones. Shor's algorithm breaks them completely. We can't just make the keys longer. We need entirely new mathematical foundations, and that means adopting lattice or hash-based post-quantum cryptography, or PQC. So, what should you actually do? Here are your actionable takeaways, especially if you're an IT or cybersecurity leader watching this. First, adopt the new NIST post-quantum cryptography standards immediately as they finalize. Second, don't just try to flip a switch overnight. Implement hybrid cryptography, which combines traditional RSA with the new PQC to create a reliable safety net. Third, upgrade your key exchanges to quantum-resistant alternatives, like Kyber. And finally, design your architecture for cryptographic agility. You need the ability to swap out encryption protocols seamlessly as new threats emerge. These steps are absolutely crucial. They're the necessary bridges to a resilient future. Because the reality is, the hardware is scaling rapidly, the algorithms are completely proven, and our transition window is closing fast. The quantum clock is ticking loudly. The only question left is, will your data be ready for the post-quantum world? Thank you so much for joining me on this explainer. Keep learning, keep preparing, and I'll see you next time as we continue to unpack the future of technology.